Longitudinal multiparametric MRI is the backbone of modern oncology follow-up, especially for brain tumors. But if you've ever worked with real-world clinical data, you know it's messy. Sequences drop out. Scanners change. Resolution and acquisition protocols drift across time points. Even after rigid registration, voxel-wise comparison becomes a nightmare because you're forced to resample everything onto a fixed grid, which introduces interpolation artifacts and destroys native acquisition characteristics. This paper tackles that exact problem by replacing discrete voxel grids with a continuous, patient-specific implicit neural representation. Instead of treating MRI as a static 3D tensor, the model learns a continuous function that maps spatial world coordinates, normalized time, and modality conditioning directly to image intensities. That shift from discrete to continuous is what makes missing sequence imputation, spatial upsampling, and temporal interpolation possible without ever touching a fixed grid. Let's break down how the architecture is built, how it's trained to handle incomplete data, and why the confidence estimation method actually matters for clinical deployment. The input to the network is a 91-dimensional vector that bundles 3 distinct signals. First, spatial coordinates in millimeters are encoded using a multi-resolution hash grid. The continuous 3D position is scaled across 16 resolution levels. At each level, features are retrieved from a learnable embedding table and combined via trilinear interpolation. With 4 channels per level, this produces a 64-dimensional spatial embedding that captures fine anatomical detail without grid quantization. Second, time is normalized to a 0 to 1 range, with a known mapping to days post-surgery. Rather than feeding a raw scalar, the model uses Fourier positional encoding with 8 frequency bands. That gives you 17 dimensions, sine and cosine terms at increasing frequencies. This allows the network to resolve subtle, nonlinear temporal changes that a linear time coordinate would completely miss. Third, and this is critical for real-world data, is the modality conditioning vector. At any given time point, not all sequences are available. The model defines a binary flag for each of the 5 modalities: T1, T1CE, T2, flare, and ADC. If a sequence is present, the flag is 1, and its intensity is passed in. If it's missing, the flag is 0. Since 0 is a valid normalized intensity, those binary flags are what disambiguate genuine 0-valued voxels from actually missing data. Combined with the intensities, that's 10 additional dimensions. All 3 encodings are concatenated and fed into a fully connected multi-layer perceptron, with 5 hidden layers of 256 units each. RayLU activations drive the nonlinearity, and a mid-layer skip connection concatenates the original embedding with intermediate activations to stabilize gradient flow. The network outputs a 5-dimensional vector representing the predicted intensity for every modality simultaneously. But how does it learn to reconstruct missing sequences without overfitting to the ones it sees? Deterministic masking would just teach the model to ignore certain input slots. Instead, the authors use stochastic modality dropout. During training, at each optimization step, a non-empty strict subset of the available modalities is randomly removed from the conditioning input. The network is then forced to predict those dropped sequences using only the remaining context. The loss is computed exclusively on the masked modalities and averaged across the batch. This creates a diverse distribution of conditioning combinations, forcing cross-modal consistency and preventing trivial identity mappings. It's a clean, elegant way to simulate real-world acquisition variability during training. Now, a model that predicts missing data is only useful if you know when to trust it. The paper derives a self-consistency-based confidence estimator directly from inference behavior. At any given time point, for each available context modality, the model temporarily removes it from the conditioning vector, reconstructs it from the remaining sequences, and computes a similarity score against the ground truth. They use either normalized mean squared error or multiscale structural similarity. The overall confidence is defined as the geometric mean of those similarity scores across all available modalities. The intuition is straightforward. If the model can reconstruct its known inputs with high fidelity, it's likely confident in its reconstruction of the missing ones. No Bayesian approximations, no Monte Carlo sampling, no ensemble overhead. Just internal consistency as a proxy for uncertainty. The evaluation focuses on 5 pediatric brain tumor patients, with roughly 9 postoperative time points each. For each patient, an interior time point is held out, and one modality is masked at inference to test both temporal interpolation and cross-modal imputation. The baseline is simple linear interpolation of available intensities across time. The results show a clear advantage for the implicit representation. Across T1CE and flare, the INR achieves statistically significant improvements over linear interpolation, with p-values below 0.05, using Wilcoxon-Seindrang tests with Benjamini-Hochberg correction. T1CE reconstruction hits a mean MSSSIM of 0.95, compared to 0.85 for the baseline. The model preserves anatomical boundaries and contrast dynamics without the blurring that voxel-wise interpolation inevitably introduces. ADC shows smaller gains, which makes sense given its different contrast mechanism and lower signal-to-noise ratio in pediatric cohorts. The confidence estimator also tracks true reconstruction quality remarkably well. Pearson correlation between predicted confidence and actual MSSSIM ranges from 0.955 to 0.985. When looking at absolute calibration, MSSSIM-based confidence shows excellent concordance with ground truth, while NMSE-based scores exhibit moderate agreement, suggesting that structural similarity is a more reliable calibration target for this architecture. There are limitations, and they're worth being explicit about. The cohort is small, which is common in specialized pediatric neuro-oncology datasets, but it restricts generalization claims. The evaluation is strictly interpolation, meaning the model hasn't been tested on temporal extrapolation beyond observed time points. Future work will likely explore pretraining strategies across larger cohorts, longitudinal tissue modeling, and explicit uncertainty quantification for recurrence detection. Still, as a proof of concept for handling heterogeneous, incomplete longitudinal MRI, the framework is compelling. What makes this approach stand out isn't just the architecture, but the design philosophy. By operating in continuous coordinate space, the model sidesteps grid alignment entirely. By using stochastic modality dropout, it learns robust cross-modal dependencies under real-world missingness. And by deriving confidence from self-consistency, it provides a deployable uncertainty signal without heavy computational overhead. As medical AI moves from controlled datasets to messy clinical pipelines, methods that natively accommodate heterogeneity will become the standard, not the exception. If you're working on longitudinal imaging, missing modality synthesis, or coordinate-based neural fields, this paper is worth a deep read. The code is open source, the methodology is reproducible, and the shift toward continuous, patient-specific representations is a clear direction for the field. Let me know in the comments which part of the architecture or training strategy you'd want to extend next, and I'll see you in the next breakdown.